Look around you. What do you see? Perhaps a glowing screen, lights illuminating your room, or the device in your hand connecting you to the world? All these marvels, and indeed much of the universe itself, are governed by a fundamental force. It's a force so pervasive, so integral to the fabric of existence that we often take it for granted. This force is electromagnetism. It's one of the four fundamental forces of nature alongside gravity, the strong nuclear force, and the weak nuclear force. While gravity holds planets in orbit and stars together, electromagnetism is the architect of atoms, the shaper of molecules, and the engine of modern technology. It dictates how light behaves, how electricity flows, and how magnets attract or repel. It is truly an unseen power that shapes our everyday lives in countless ways. Understanding electromagnetism is like gaining a key to unlock many of the universe's deepest secrets. It's the force responsible for the structure of matter itself. The atoms that make up your body, the air you breathe, and the ground beneath your feet are all held together by electromagnetic interactions between charged particles. Without it, electrons wouldn't orbit atomic nuclei, and chemistry, as we know it, simply wouldn't exist. Life itself, in all its complex biochemical glory, is a testament to the power and subtlety of electromagnetism. It's the glue holding our world together, from the smallest subatomic particles to the grandest technological achievements. This force is not just about light bulbs and refrigerators, it's about the very essence of physical reality. The journey into understanding this force has been a long and fascinating one, marked by brilliant minds who pieced together clues from the natural world. From ancient observations of static electricity and lodestones to the sophisticated theories of the 19th century, humanity has slowly unveiled the dual nature of electricity and magnetism and their profound interconnectedness. This journey of discovery has not only expanded our knowledge of the cosmos but has also revolutionized our civilization. Every time you flip a switch, make a call, or even see a rainbow, you are witnessing the effects of electromagnetism at play. It's a silent partner in almost every aspect of your daily experience. In this exploration, we will delve into the nature of this remarkable force. We will examine its two fundamental components, electric fields and magnetic fields. We will see how these fields interact and give rise to the phenomenon of electromagnetic waves, which include everything from radio waves to visible light to X-rays. And we will marvel at how our understanding of this force has enabled us to build the technological world we inhabit today. Prepare to see the universe and your place within it in a new light, an electromagnetic light, if you will. The story of electromagnetism is a story of power, connection, and the relentless human quest for understanding. At the heart of electromagnetism lies the concept of electric charge. You've likely experienced it yourself. Perhaps a shock after walking across a carpet, or the way a balloon sticks to a wall after being rubbed against your hair. These are manifestations of static electricity, which arises from an imbalance of electric charges. Particles in nature can possess a property called electric charge, which comes in two types, positive and negative. Protons found in the nucleus of an atom carry a positive charge, while electrons orbiting the nucleus carry a negative charge. Like charges repel each other, positive repels positive and negative repels negative. Conversely, opposite charges attract positive and negative charges are drawn towards one another. This fundamental interaction is the starting point for understanding electricity. These charged particles don't just interact when they're touching, they exert their influence across space. They do this by creating something called an electric field. An electric field is an invisible region of influence surrounding any charged object. Think of it as an aura that extends outwards from the charge. If you place another charged particle within this field, it will experience a force, either an attraction or a repulsion, depending on the nature of its own charge and the charge creating the field. The strength of this electric field is greatest near the source charge and diminishes as you move further away. We can visualize electric fields using lines of force, which point in the direction a positive test charge would move. The creation of an electric field is an intrinsic property of charged particles. A single electron sitting all by itself generates an electric field that stretches out into the space around it. Similarly, a proton does the same. The more charge an object possesses, the stronger the electric field it generates. Consider a thundercloud, where an enormous amount of charge can accumulate. This creates a tremendously powerful electric field between the cloud and the ground, or between different parts of the cloud. When this field becomes strong enough, it can overcome the insulating properties of air, resulting in a dramatic discharge of electricity, a lightning bolt. This is a spectacular display of electric fields at work on a grand scale. Understanding electric fields is crucial because they're not just static phenomena. They can change, they can move, and as we will see, their interaction with magnetism is what truly unleashes the power of electromagnetism. The flow of electric charge, which we call electric current, is essentially charges moving under the influence of an electric field, often guided through conductive materials like wires. Every electrical appliance you use, from your toaster to your computer, relies on the carefully controlled generation and manipulation of electric fields to make charges move and do useful work. Electric fields are the unseen puppeteers, directing the dance of charges that powers our modern world. Now, let's turn our attention to the other half of this dynamic duo: magnetic fields. Like electric fields, magnetic fields are also invisible regions of influence, but they arise from a different source. While static electric charges create electric fields, magnetic fields are primarily generated by moving electric charges or electric currents. This is a key distinction. A stationary electron creates an electric field, but if that electron starts moving, it also generates a magnetic field around its path of motion. This intrinsic connection between electricity and magnetism is fundamental to understanding the combined force of electromagnetism. It hints at a deeper unity that wasn't immediately obvious to early investigators. You are probably most familiar with magnetic fields from permanent magnets like the ones that stick to your refrigerator. These magnets have two poles, a north pole and a south pole. Similar to electric charges, like poles repel each other, north repels north, south repels south, and opposite poles attract, north attracts south. If you break a bar magnet in half, you don't get isolated north and south poles. Instead, you get two smaller magnets, each with its own north and south pole. This is a fundamental difference from electric charges, where positive and negative charges can exist independently. Magnetic poles always seem to come in pairs, a phenomenon described by the absence of magnetic monopoles. The Earth itself is a giant magnet, with its own magnetic field extending far out into space. This geomagnetic field is generated by the movement of molten iron in the Earth's outer core, a massive system of circulating electric currents. This field is incredibly important for life on Earth, as it deflects harmful charged particles from the sun, known as the solar wind, protecting our atmosphere and us. The aurora borealis and aurora australis, the beautiful northern and southern lights, are a stunning visual manifestation of these charged particles interacting with the Earth's magnetic field and atmosphere. It's a cosmic light show, powered by magnetism on a planetary scale, a reminder of the vast forces at play. While permanent magnets are fascinating, the ability of electric currents to create magnetic fields is what truly revolutionized technology. A simple wire carrying an electric current generates a circular magnetic field around it. If you coil that wire, the magnetic field becomes concentrated and stronger, especially if you place an iron core inside the coil, creating an electromagnet. This principle allows us to create powerful and controllable magnetic fields, which are the basis for countless devices, from electric motors that power our appliances to the loudspeakers that bring us music and sound. The interplay between moving charges and the magnetic fields they produce is a cornerstone of electromagnetic phenomena. For centuries, electricity and magnetism were studied as separate, albeit intriguing, phenomena. Static electricity had its own set of rules, and magnetism had its distinct characteristics. Observers noted some curious parallels, like the attraction and repulsion laws, but a deep, unifying theory was missing. Then, in the 19th century, a series of experimental discoveries began to reveal the profound connections between these two forces. Scientists like Hans Christian Ørsted discovered that an electric current could deflect a compass needle, demonstrating that electricity could produce magnetism. Michael Faraday then showed the reverse. A changing magnetic field could induce an electric current in a wire, a phenomenon known as electromagnetic induction. These were groundbreaking revelations. These experimental findings provided crucial pieces of the puzzle, but it was the brilliant theoretical physicist James Clerk Maxwell who, in the 1860s, wove them all together into a single, comprehensive theory of electromagnetism. Maxwell formulated a set of 4 elegant equations, now famously known as Maxwell's equations. These equations mathematically described how electric and magnetic fields are generated and how they interact with each other and with charges and currents. They showed that electricity and magnetism were not separate forces at all, but rather two aspects of the same fundamental force, the electromagnetic force. This was a monumental achievement in physics, comparable to Newton's laws of motion and universal gravitation. Maxwell's equations did more than just unify electricity and magnetism, they made an astonishing prediction. They showed that a changing electric field creates a changing magnetic field, and conversely, a changing magnetic field creates a changing electric field. This interplay means that these fields can generate each other, propagating through space as a wave, an electromagnetic wave. Even more remarkably, Maxwell calculated the speed of these waves based on electrical and magnetic constants measured in the laboratory. The speed he calculated turned out to be the speed of light, which had already been measured with considerable accuracy. This was no coincidence. This led to the revolutionary conclusion that light itself is an electromagnetic wave. This was a profound insight, unifying optics with electricity and magnetism. It revealed that the visible light our eyes perceive is just one small part of a vast spectrum of electromagnetic radiation, all traveling at the same incredible speed in a vacuum, approximately 300,000 kilometers per second, or 186,000 miles per second. Maxwell's work not only provided a complete theoretical framework for understanding electromagnetism, but also opened the door to understanding the nature of light and predicting the existence of other forms of electromagnetic waves, which were later discovered experimentally by Heinrich Hertz. His theory was a symphony of physics, harmonizing disparate phenomena into one beautiful whole. Section 5: Generating waves ripples in the fabric of spacetime. Maxwell's equations elegantly predicted that these intertwined electric and magnetic fields could sustain each other, propagating outwards as electromagnetic waves. But how are these waves actually generated? The key lies in accelerating electric charges. A stationary charge creates a static electric field. A charge moving at a constant velocity, a steady current, creates both a static electric field and a static magnetic field. However, if you make a charged particle wiggle or oscillate back and forth, that is, accelerate it, then things get really interesting. This acceleration causes the electric field around the charge to change, and this changing electric field in turn generates a changing magnetic field. This newly created changing magnetic field then generates a new changing electric field a bit further away, which then generates another changing magnetic field, and so on. It's a self-perpetuating dance, a cascade of energy rippling outwards from the source. These propagating disturbances in the electromagnetic field are what we call electromagnetic waves. They don't require a medium to travel through. They can traverse the vacuum of space, which is how light from the sun and distant stars reaches us. The energy of the wave is carried in these oscillating electric and magnetic fields, which are perpendicular to each other and also perpendicular to the direction the wave is traveling. Think of an antenna transmitting a radio signal. Inside the antenna, electrons are forced to oscillate rapidly up and down. This acceleration of charges launches electromagnetic waves into the surrounding space. The frequency of the oscillation of the charges determines the frequency of the electromagnetic wave produced. Higher frequencies mean the charges are wiggling faster, and this corresponds to waves with shorter wavelengths and higher energy. Conversely, lower frequencies correspond to longer wavelengths and lower energy. This relationship between frequency, wavelength, and energy defines the entire electromagnetic spectrum. These waves carry energy and information across vast distances. When an electromagnetic wave, like a radio wave, encounters another conductor, such as a receiving antenna, the oscillating electric and magnetic fields of the wave can exert forces on the charges within that conductor. This causes the charges in the receiving antenna to oscillate in sync with the incoming wave, generating a tiny electric current. This current can then be amplified and decoded to retrieve the information encoded in the wave, whether it's music, a voice, or data. This principle of generating and receiving electromagnetic waves is the foundation of all wireless communication technologies. Section 6. The electromagnetic spectrum, a universe of light. The realization that light is an electromagnetic wave was just the beginning. Maxwell's theory implied that there should be a whole spectrum of such waves, differing only in their frequency and wavelength. And indeed, this vast electromagnetic spectrum encompasses an incredible range of radiation types, each with its unique properties and applications. At one end of the spectrum, we have radio waves, with the longest wavelengths and lowest frequencies. These are used for broadcasting radio and television signals, for Wi-Fi, Bluetooth, and for radar systems that can detect airplanes or track weather patterns. Their ability to travel long distances and pass through obstacles makes them ideal for communication. Moving up in frequency and down in wavelength, we encounter microwaves. These are familiar from microwave ovens, where they efficiently heat food by causing water molecules to vibrate. Microwaves are also crucial for satellite communication and for mobile phone networks, carrying vast amounts of data across the globe. Next comes infrared radiation, which we perceive as heat. All objects with a temperature above absolute zero emit infrared waves. Night vision goggles work by detecting infrared radiation, allowing us to see in the dark. Remote controls for your television also use pulses of infrared light to send signals. Then we arrive at the narrow band of visible light, the only part of the electromagnetic spectrum that our eyes can detect. This tiny sliver of the spectrum, ranging from red, the longest visible wavelength, to violet, the shortest visible wavelength, is responsible for all the colors we see in the world around us. Beyond violet light lies ultraviolet or UV radiation. The sun is a powerful source of UV rays, which can cause sunburns and skin damage with prolonged exposure. However, UV light also has beneficial applications, such as sterilizing medical equipment and in certain industrial processes. It's also what causes some materials to fluoresce. At even higher frequencies and shorter wavelengths, we find X-rays. Discovered by Wilhelm Conrad Röntgen, X-rays have the ability to pass through soft tissues, but are absorbed by denser materials like bones, making them invaluable for medical imaging and for inspecting materials in industry. Finally, at the highest frequencies and shortest wavelengths, we have gamma rays. These are the most energetic form of electromagnetic radiation, typically produced by nuclear reactions, such as those occurring in nuclear explosions, radioactive decay, or in extreme astrophysical events like supernovae. Gamma rays are highly penetrating and can be dangerous, but they also have applications in cancer treatment or radiotherapy and in sterilizing medical supplies. This entire spectrum, from radio waves to gamma rays, is all fundamentally the same phenomenon: electromagnetic waves, just vibrating at different rates. Section 7. Power and motion, motors and generators. The deep connection between electricity and magnetism, so elegantly described by Maxwell, has not only revolutionized our understanding of the universe, but has also powered the modern industrial world through two incredibly important inventions: the electric motor and the electric generator. These devices are essentially mirror images of each other in terms of the energy conversion they perform, both relying on the principles of electromagnetism. An electric motor takes electrical energy and converts it into mechanical energy, producing motion. A generator, conversely, takes mechanical energy and converts it into electrical energy. Together, they form the backbone of our electrified society. Consider the electric motor. It works because of the force exerted on a current-carrying conductor when it is placed in a magnetic field. This is known as the Lorentz force. In a typical motor, coils of wire, the armature, are placed within a magnetic field, often created by permanent magnets or electromagnets, the stator. When an electric current flows through these coils, the magnetic field exerts a torque or twisting force on them, causing the armature to rotate. This rotation can then be used to do useful work such as spinning a fan, powering a blender, driving an electric car, or operating heavy machinery in factories. The simplicity and efficiency of electric motors have made them ubiquitous. Electric generators, on the other hand, operate on Michael Faraday's principle of electromagnetic induction. Faraday discovered that if you move a conductor through a magnetic field or change the magnetic field around a stationary conductor, a voltage, and thus a current if there's a complete circuit, is induced in the conductor. In a practical generator, a coil of wire, the rotor, is made to spin within a magnetic field. This continuous change in the magnetic environment experienced by the coil induces an electric current. The mechanical energy required to spin the rotor can come from various sources such as steam turbines powered by burning fossil fuels, nuclear reactions or geothermal heat, water turbines in hydroelectric dams, or wind turbines. The electricity generated in power plants is then transmitted over vast networks of power lines to homes, businesses, and industries. This large-scale generation and distribution of electrical power would be impossible without our understanding of electromagnetism. Every time you plug an appliance into an outlet, you are tapping into a vast system built upon the principles discovered by Faraday and Maxwell. From the smallest motors in your wristwatch to the colossal generators in power stations, electromagnetism is constantly at work, converting energy from one form to another, making our lives more convenient, productive, and comfortable. The dance between electric and magnetic fields truly powers our world. Section 8. Peering inside. Electromagnetism in medicine. Beyond powering our homes and industries, electromagnetism plays a profoundly important role in medicine, allowing us to diagnose illnesses, peer inside the human body non-invasively, and even treat certain conditions. One of the earliest and most well-known applications is the X-ray. As we discussed, X-rays are high-energy electromagnetic waves that can pass through soft tissues but are absorbed by denser materials like bone. This property allows doctors to create images of the skeletal system, identify fractures, and detect abnormalities like tumors or foreign objects within the body. Dental X-rays help find cavities, and mammograms use X-rays to screen for breast cancer. It's a window into the body, opened by our control over this specific part of the electromagnetic spectrum. Another remarkable medical imaging technique that relies heavily on electromagnetism is magnetic resonance imaging, or MRI. Unlike X-rays, MRI does not use ionizing radiation. Instead, it uses a powerful magnetic field, radio waves, and sophisticated computing to create detailed cross-sectional images of organs, soft tissues, bone, and virtually all other internal body structures. The patient is placed inside a strong magnet, which aligns the protons within the body's water molecules. Radio waves are then pulsed, temporarily knocking these aligned protons out of alignment. As the protons relax back into alignment, they emit faint radio signals that are detected by the MRI scanner and used to construct highly detailed images. Electromagnetism is also used directly for therapeutic purposes. For example, radiotherapy uses high-energy X-rays or gamma rays to target and destroy cancerous cells. The radiation damages the DNA of the cancer cells, preventing them from growing and dividing. Another technique, called transcranial magnetic stimulation, or TMS, uses rapidly changing magnetic fields to induce small electric currents in specific regions of the brain. TMS is being explored and used as a non-invasive treatment for conditions like depression, anxiety, and Parkinson's disease. Even something as common as an electrocardiogram, or ECG, which records the electrical activity of the heart, relies on detecting the tiny electrical signals generated by heart muscle contractions. Furthermore, techniques like electrosurgery use high-frequency electric currents to cut tissue or seal blood vessels during operations, minimizing bleeding. Defibrillators deliver a controlled electric shock to the heart to restore a normal rhythm during cardiac arrest. Even the basic diagnostic tools used by doctors, like otoscopes to look into ears or ophthalmoscopes to examine eyes, often incorporate light sources, which are, of course, a form of electromagnetic radiation. The applications of electromagnetism in medicine are vast and continue to expand, providing doctors with incredible tools to diagnose, treat, and improve human health, all thanks to our understanding of this fundamental force. Section 9. Conclusion: the ever-present force shaping our world. As we've journeyed through the realm of electromagnetism, from the fundamental nature of electric and magnetic fields to their grand cosmic dance as electromagnetic waves, one thing becomes abundantly clear: this force is not just an abstract concept confined to physics textbooks. It is an active, dynamic, and utterly essential component of our universe and our daily lives. It is the invisible architect that structures matter, the silent messenger that carries information across the cosmos and across your room, and the tireless workhorse that powers our technological civilization. Without electromagnetism, the world as we know it simply could not exist. Our understanding of it has truly transformed humanity's capabilities. Think about a typical day. You wake up, perhaps to an alarm clock powered by electricity. You turn on the lights, visible electromagnetic radiation. You might listen to the radio or watch television, receiving signals carried by electromagnetic waves. Your mobile phone, connecting you to a global network, operates on these same principles. The car you drive, if it's a conventional one, uses an electric spark to ignite fuel, and its battery relies on electrochemical processes. If it's an electric vehicle, its very motion is a direct application of electromagnetic motors. The food you eat is often cooked using devices that rely on electricity or microwaves. Every click, every call, every illuminated screen is a testament to our mastery over this force. The journey of discovery, From ancient curiosities about amber and lodestones to Maxwell's unifying equations and beyond, represents one of the greatest intellectual achievements of humankind. This understanding has not only satisfied our innate curiosity about how the universe works, but has also equipped us with the tools to innovate and create technologies that have profoundly improved the quality of life for billions. From life-saving medical imaging techniques like MRI and X-rays to the global communication network that connects us all, electromagnetism is the common thread. It's a force that binds atoms, illuminates galaxies, and powers progress. So the next time you see a rainbow, feel the warmth of the sun, or simply flip a switch, take a moment to appreciate the incredible power of electromagnetism. It is a fundamental force of nature, elegant in its principles and astonishing in its manifestations. It's a reminder that the universe operates on a set of profound, interconnected laws, and that our ongoing quest to understand these laws continues to unlock new possibilities and reshape our world. Electromagnetism is more than just science. It is the invisible engine of modern existence, constantly at work, shaping our present and illuminating our future.